Hi everybody, my name is Anis Matunga, aka Dr. Ghost. I'm so excited to be with you today as we look at the action potentials. So let's get into it. I thought it would be easier for us to understand action potential if we understand the basic structure of a neuron and how it takes place in the transmission of signals. So basically, we have the dendrites that receive signals. Then we have the cell body that integrates it, and then we have the axon that transmits the signal received from the dendrites, and then we have the myelin sheath. So the myelin sheath are insulators that coat around axons, and then we have the node of Ranvier that is created by the space between those myelin sheaths that are coating the axon. And this actually is very important for saltatory conduction, which is jumping of transmission, which I'll be explaining in a few minutes. We also have the axon terminals and the synapse. So the axon terminals is where the transmission terminates and it is passed on to the next cell at the synapse. Okay, so we're going to take a closer look at the axon, and as you can see in the picture, we have two myelin sheath cells on each side, and at the center we have our node of Ranvier. And right now we're going to look at the node of Ranvier. As you can see on the node of Ranvier, there are high density of voltage gated sodium channels, okay? And if you look at the axon, if you look at the axon under the myelin sheath, it does not have those sodium gated channels. So when signal is reaching the node of Ranvier, right, those sodium gated channels open and sodium rushes in, which is called sodium influx, and depolarization happens there. So this generates the action potential, which then passively spreads under the next myelin sheath segment to the next node of Ranvier. And one thing you must also know is that the Schwann cells and oligodendrocytes are usually the ones that make up the myelin sheath. Schwann cells, which are found in the rest of the body, and then oligodendrocytes are found in the spinal cord or in the brain. So the next thing we're going to talk about is saltatory conduction. And saltatory conduction comes from the Latin word salte. Salte, or salta, I don't know how you would pronounce it, means jumping. So basically, saltatory conduction is the jumping of impulse from one node of Ranvier to the next, which helps speed up the rate of electrical conduction, and it becomes more efficient. So the action potential doesn't travel straight down continuously the axon. It jumps from one node to the next, which I've already said, and the myelin sheath blocks the inflow so that the signal only regenerates at the node of Ranvier, where the sodium gated channels are located. This makes the conduction much faster and much more efficient, right? So what really happens at the node? Okay, so I want you to pay attention to two very important terms, which is influx and efflux. The word in should guide you that this is something flowing inward, and then efflux referring to something leaving, which is the opposite of influx. So just remember that even in your exam, this will really help you to just know that sodium influx causes depolarization, and potassium efflux causes repolarization at the node of Ranvier, you understand? So potassium ions leave, that causes repolarization. Sodium ions flow inwards, which is influx, causes depolarization. I will show you shortly on the graph. The graph is drawn there and it's not that big and you might not make sense of it, but I'll show you shortly on the graph and you get to understand. The other thing I want you to know is the two refractory periods, which is the absolute refractory period, which is when the sodium gated channels are inactivated. This allows the node to not fire immediately after it has fired an impulse. And there's also relative refractory period, which makes it really difficult for the node of Ranvier to fire because the membrane is hyperpolarized. So if you hear hyperpolarized membrane, just know it's relative refractory period. If you hear absolute refractory period, you think of sodium gated channels that are inactivated. This is important because it ensures one-way propagation. Signal does not move backwards. It can only move in one direction. It does not move backwards, which is forward basically. So yeah, and then other key things we must just know and always remember is that action potential only occurs at the node of Ranvier, okay? Anything that happens under the myelin sheath is only the spread, a passive spread of impulses. It's also important to note that unmyelinated axons have continuous conductions which are slower and use more energy. And as we said, the myelinated ones have saltatory conduction, that is faster and uses less energy, which is saltatory, which I said means jump, right? So let's move on. Okay, so this is our graph showing the action potential. On our y-axis, we have the membrane potential per millivolt, and then we have time, okay? So this shows the step-by-step flow of electrical impulse in the axon per time, okay? So as you can see, we start with our resting membrane potential, which is at about minus 70 millivolts, and the neuron is just chilled there. There is no signals being transmitted. Everything is just, at rest, okay? Because it's called resting membrane potential anyway. Now, stimulus comes in, okay? Maybe from another axon or from another neuron, and it does not reach the threshold, okay? So we'll have small stimuli that keep coming and coming and coming until the stimuli reach, according to our graph, negative 55 millivolts. We'll then have a threshold, okay? So before it reaches negative 55 millivolts, we do not have a threshold, so nothing happens. We just have small tiny graphs there that shows that this impulse or this stimuli is below threshold. So it's only the one that reaches the threshold of minus 55 millivolts that then shoots or spikes and causes a depolarization. And remember what I said. As a depolarization is as a result of sodium gated channels opening, and positively charged sodium rushes into the axon, okay? The voltage shoots right up all the way to plus 30 millivolts, and that's the peak of the action potential, as you can see on the graph. Now that we're at the peak, repolarization must take place, okay? So sodium gated channels close. That means sodium stops flowing in, right? But then what happens? What happens is now we have potassium efflux. And what did we say about efflux meant? It means flowing out. So potassium channels open and potassium leaves the axon area, okay? So potassium flows out of the cell, okay? And this brings back the resting potential to its normal levels. But now, note that there is a dip, okay, that exceeds the minus 70, which is our resting membrane potential, and that is considered as hyperpolarization. What happens is, as our potassium is leaving, the potassium channels closes slowly, okay? The potassium channels don't just shut like sodium channels. Potassium channels are a bit slow to close, and that causes the hyperpolarization, which causes the charge to go way below our resting membrane potential, which is negative 70 millivolts. So it goes somewhere around negative 80, negative 90, and that causes what? Our hyperpolarization. And then after our hyperpolarization, our potassium channels close, and our sodium pump then helps to rest everything back to normal, and we bring back our resting membrane potential to about negative 70 millivolts, and we're back to rest. We're waiting for our next signal so that this happens again. Okay, so I've created these short notes for you to just go through and understand. So just pause and review, and I hope it becomes more clearer for you. So, but basically the roundup is we have stimulus that then hits threshold, and then we have depolarization, repolarization, hyperpolarization, and from there we rest. That's basically it. And then we're done. I also added some few notes or extra notes on the refractory period, which I mentioned that there's absolute refractory period, which occurs during depolarization or early repolarization. And this is where no new action potential can be initiated because the sodium gated channels are closed. But then relative refractory period, which happens during the late repolarization or during the hyperpolarization, happens mainly because the potassium gated channels are still open, and sodium channels, some have recovered, but they're still closed. So basically, this sums everything up. And I hope you understood. If you have questions, feel free to ask. This was fun. It took me a little longer to make this video. I have not been feeling so well, but I'm glad I finally finished it and I get to post it. I'm so excited. I hope you guys are having a wonderful day. Love from me. Bye. Till next time. Don't forget to like, love, and subscribe.